All right, on to one of the cooler things that I like to talk about with waves, the Doppler effect, or because we're up here in Boston, the Doppler effect, Doppler, the Doppler, the Doppler radar. South side's telling us it's sunny. This storm coming in because of the Doppler. Anyway, sorry. So we're going to take a look at what that is. You've absolutely heard it before. You not heard of the word, but I mean you have actually experienced the Doppler effect before. I guarantee you. And we're going to check back in with our friend Charlie is so cool like, which I did some research between after our last video. He is still out there. He's made a bunch more fun science videos. Some of them have to do with us. A lot of them don't have to do with us, which is sad. But you should totally check him out on YouTube. Charlie is so cool like, all one word. He's pretty awesome. He's got some great stuff. And this one is definitely by far like way better than his song one. Like the amount of stuff he does in here is great. So without further ado, let's get into it. Here's the Doppler effect. Let's do that again. Let's do it one more time. That's the Doppler effect. The observed change in frequency due to relative motion between any wave source and an observer. Oh, Mr. T, you just read text off your own video. Yeah, I know. But I wanted to highlight that because I wanted to put the emphasis there on observed, meaning it's not an actual change in frequency of the wave. The wave source does not change. If you were in that car, you would just hear that same the whole time. The only reason why we heard something different is because there was relative motion between us and the source, meaning that the source was moving. We could have been moving too. Like if instead we were in a car honking our horn and that car drove by, then the car would hear something different, which is kind of interesting. Because we would be the stationary wave source, but there'd be relative motion, meaning like one of them is moving in relation to the other. And this is something that happens very, very frequently and happens so much that they actually started programming it into sirens. Like sirens just used to be like, wah! But people would hear this and think that sirens need to go wah, wah, wah. So let's hear the Doppler effect on top of the Doppler effect. So, what we notice here is that as the wave source is moving towards us, or as the relative motion is getting closer to each other, right? The relative, you can either be moving towards each other or away from each other. And when we're moving towards each other, we hear a higher pitch sound or a higher frequency sound. As it passes us, it turns into a lower frequency sound. So we observe this either higher frequency wave or lower frequency wave. I'm being very careful to say observe a higher frequency or lower frequency wave. And you'll see why in a minute. Spoiler. So here's what's happening. In this first picture here, we have what a wave would look like being transmitted uniformly. Right, so any sound wave we know goes out in all directions. We've talked about this before. I make a sound. Doesn't matter if you are here or here, you hear the same sound because the sound goes out uniformly from my face. The only difference would be is if you were on the opposite side. So when I talk like this, you hear a different sound because the sound is not directed towards you. It's directed that way. But you can still hear it because it bounces back off and still vibrates all the rest of the air out here, and it will eventually get to you. You just hear it more clearly because it's coming directly at you in the microphone right now, because I have smartly positioned the microphone directly behind the camera, because, that's where I'm talking. But here's what happens when you've got a wave source that's moving, right? So it starts off, the waves are still being shot out uniformly, just like here. There's no difference. Right? But because you're moving into the waves you're creating on this side, those waves, those compressions or whatever the wave is actually getting squished together. That appears to be happening more frequently. And what's happening on the backside is you're moving away from those waves. So it looks like there's more space in between them, even though there's not. You're still just doing this. But a relative observer would still experience those would experience them this way. If you were in the car with the horn, like we talked about, you would just hear this because there is no relative motion. The horn and you are moving at the same speed, so you get those waves coming out uniformly. But someone stationary hears this. As it's moving towards you, you hear the higher frequency sound, and then as it moves away from you, it turns into that lower frequency sound, which is cool. And so here's kind of an example again, looking from a side view. Right? So as that wave source moves, right, it's still making those waves at the exact same frequency, but towards you, the wave is squished together, and when it's moving away from you, the wave is stretched out. And that's all there really is to the Doppler effect. Nice, quick, short video. No, just kidding. It's not over. There's far more to it than that.
Now, before I tell you about all of the really cool stuff that comes with light and the speed of light, I have to tell you about this other thing called the Doppler Effect, which is still really interesting, so, don't leave just yet. The Doppler Effect is the change that you notice in the frequency of a wave when the source of that wave is moving relative to you. For example, imagine that you're sitting by a canal enjoying the lovely British weather when suddenly I appear next to you screaming like a lunatic. From your perspective, it's just really, really weird. However, if theoretically I wasn't standing next to you but was running past you at 80 miles an hour, still screaming just as I was before, as I approach you, the pitch of my scream would be higher, and then as I pass and run away from you, the pitch of my scream would drop, even though from my perspective, I'm screaming at exactly the same pitch as I was when I was standing still.
Imagine if you could do that. Now, you can't do that because the amount of Doppler effect that you get is based on how fast you're moving relative to the speed of that wave. Now, humans cannot run very close to the speed of sound. Like, speed of sound is about 300 meters per second, 343 in air, usually. That's no, too fast. We can't run that, even remotely that fast. So normally when we're just running, we don't hear a huge difference. But cars can travel a lot faster than us, which is why we can actually, observe that effect. Not because they're getting really close to the speed of sound, but they're traveling close enough to the speed of sound to where we can actually observe with our ears that change in frequency. It's very, very noticeable. But humans can't run that fast, unfortunately. I wish. That'd be so cool. That'd be hilarious.
The reason this shift in pitch happens is because when I'm sitting still and screaming, the sound waves are emitting from my mouth uniformly. But when I start moving, the sound waves in front of me get squished up and the sound waves behind me get stretched out. And it's this change in the frequency that causes the change in pitch as I pass, and that is what the Doppler effect is. The reason the Doppler effect is important is because it doesn't just apply to sound, but it also applies to light. Bet you didn't see that one coming, because it's not a video about light or anything like that, is it?
Actually, Charlie, we didn't know that because we're not watching this on YouTube. We're watching this in... Actually, you might kind of be watching this on YouTube, but you're watching this within another YouTube video, so they didn't get to see the title of the thing. It's called Fun Science Light, by the way. That was the joke, which I've now made even less funny. Sorry.
So just as when something is moving and emitting sound, you can hear a difference in the pitch of that sound, when something is moving and emitting or reflecting light, you can see a difference in the colour of that light. For example, imagine that we're in exactly the same running canal situation as before, except this time I'm not screaming like a lunatic, and instead of running at 80 miles an hour, I'm running at very, very nearly almost the speed of light. What would you see? Well, you probably wouldn't see anything at all, because as you'll remember, the speed of light is very, very, very fast, and I'd be gone before you even knew I was there. But let's pretend that you had a magic iPhone app that would let you take pictures of me travelling very nearly at the speed of light. What would you see? Well, when I'm running towards you, the light in front of me gets squished, and the frequency of that light gets shifted to the blue end of the visible light spectrum, and so I appear blue. And then as you see me running away from you, the same thing happens in reverse. The light behind me gets stretched out, shifts to the red end of the spectrum, and then I appear to be slightly red. Now, this change in the frequency of light is something that happens all the time. In fact, it's happening right now as I move forwards and backwards from you, but the change is so negligible that you can't notice it unless something is travelling at very, very nearly the speed of light.
And that is why I love this video, because it pauses right there on that awesomely hilarious face. Now, yeah, Doppler effect, all waves, right? That's why I was very sure it was the frequency of the wave, not the frequency of the sound. So the same way that sound waves can be Doppler shifted, light waves can be Doppler shifted. And so it's the same effect. You're going to be shifted to a higher frequency color or a lower frequency color. And we know that with Roy G. Biv, red was the longest wavelength because it had the lowest frequency, and purple was the highest frequency and the shortest wavelength. But red and blue, I guess, just kind of go together better, which is why they said red shift, blue shift, one shift fish, two shift. I don't know, Dr. Seuss. But the same effect would happen if that thing was moving fast enough, moving towards you, you would see a higher frequency color, and as you saw there, shifted kind of blue. We can rewind back to that.
Now, before I can pretend that you had a magic eye.
Okay, cool. Yeah. So, moving towards you shifted to a higher frequency color. Not completely changed, just, kind of shifted in the tint. But then as it moves away from you, shifting to a longer frequency color. Or rather, a lower frequency color. And it would be shifted red. And this is why, and this is the saddest part of remote learning right now, this would be sticker day. We would come in and we'd be like, guys, it's sticker day. The bumper sticker on the board. If you're driving too fast, or if this sticker's blue, you're driving too fast, that's why. So it's a red sticker. And that would mean that if you were driving fast enough that you could actually see the color shifted to blue, right? Because it was moving towards you, and that red frequency was shifted all the way to blue, you would be violating any kind of speed limit law there is. Because we don't see those colors. Like, we can naturally observe the Doppler effect in sound waves pretty easily, because we can get pretty close to the speed of sound. In fact, a lot of vehicles we have can go faster than the speed of sound. But we can't travel close enough to the speed of light where you would actually see a Doppler shift in the color of things. Sadly, unfortunately. Which is why that sticker is funny, because not only would you be obviously traveling, where you're violating all the speed limit rules on Earth, you'd be also violating the laws of physics, because you can't travel that fast to shift something all the way from red to blue. Just doesn't happen. Doesn't happen. But on that note of traveling faster than sound waves, that's what sonic booms are. Check this out. That would have been such a good segue. Alright, so this is a summary of like red shift, blue shift, one shift, two shift. Right, so moving towards you, just like you'd hear a higher frequency sound, you'd see a higher frequency color. Moving away from you, you'd hear a lower frequency sound, you'd see a lower frequency color. Sound emitted by the source, though, even though the train isn't green. But hopefully you get the idea from that diagram there. So that, I don't know why they don't call it red shift or violet shift, because red shift, blue shift is just, I don't know, Dr. Seuss. Doppler effect. Doppler effect. Too many slides here. Alright, this is what I'm talking about. So this dot here, is, the question is, alright, well, that, if you're traveling close to the speed of the wave, then you'll see the Doppler effect. But what if you're traveling at the speed of the wave? Well, this is what the waveform looks like. And what actually happens here is, if you're right here, you're going to hear a whole bunch of sound waves at first. And that's what the sonic boom is. It's kind of a big crack of all those sound waves kind of happening all at once that have been building up as it moves forward. Which is why when you hear jet planes go by, it's like a shoo, shoo, shoo. It's just like the super ramped up version of the meow, meow. It's just that, ramped up even more. So, here's an example. Check this out. Now, no, my video did not lag. You could see the plane here. It's this close to you. You still haven't heard it yet because all those sound waves haven't happened yet. It's traveling so fast that the sound hasn't even been able to catch up to it, which is why you don't actually hear it until it's past you. Right? Check this out again. You see it. No sound, no sound, no sound. That's crazy. That never happens. You can always hear a plane coming long before you see it. Nope. Sonic boom, baby. Check this one out. This one's pretty cool too. All of those sound waves catch up all at once. Hearing all those sound waves catch up at once. That's so cool. So yeah, that's what's happening. And then if you travel faster than that, then you get to start to be supersonic, right? So stopped, you get this kind of uniform wave pattern. Going subsonic, you'll just get the Doppler effect, You you get the speed of sound, you get that sonic boom. And then going supersonic, it's kind of similar to what you just saw there. It's just like you're going to get a huge bunch of interference there. Not just happening all at once, but it's just jumbled up business and junk. But it's all just hardcore Doppler effect, which is pretty cool. So, with that, what questions and connections do you have? Hopefully this is a nice, quick, short one. We'll see the time of it, because I have no concept of time when I'm doing these things. I don't know if they're long or short. This one felt shorter. We'll see. What questions and connections do you have? Let me know. I'm sure there's probably going to be stuff about the Doppler radar. Google it first. See what comes up. And then ask me some questions. Okay, I'll see you next time.